তোমাদের আর কেউ আসবে না শুরু করবো?
ম্যাম অ্যাকচুয়ালি মানে অনেকে বলছে যে আজকে ক্লাসটাকে একটু পোস্টপোন করা যাবে।
পোস্টপোন? তোমরাই তো আগে আনতে বললে, আমি তো 10টা থেকে বলছিলাম। আর সেরকম কিছু তো তোমরা আমাকে আগে জানাওনি।
অ্যাকচুয়ালি আমরা মানে অনেকেই জানতামই না যে মানে ক্লাসটা
জান
আছে।
সে আবার কি, আমি তো ক্লাসে 2 দিন তোমাদের বলেছি, এবং লাস্টে তো বলেছিলাম, লাস্ট ক্লাসে, তাই না? তোমাদের যে সিআর, কে তোমাদের সিআর, সে বন্ধ করেনি। লাস্ট ক্লাস হয়েছে 26 সম্রাট ছিলে তো? হ্যাঁ, তো তুমি বলনি তোমাদের বন্ধুদের? অনেকেই ছিল তোমরা লাস্ট ক্লাসে। হ্যাঁ, সম্রাট তো বলছে সবাই জানতো। তাহলে আমি অনেক আগেই বলেছিলাম। হুম ঠিক আছে, আমি তাহলে এখন 8:10 বাজে আমি শুরু করছি তোমাদের। স্ক্রিন শেয়ার হলে একটুখানি বলবে যে শেয়ার হয়েছে, হ্যাঁ। আর চ্যাটে লিখো না, কারণ স্ক্রিন শেয়ার হয়ে গেলে আমি বিয়েটা দেখতে পাবো না, চ্যাটটা মুখে বলো। আচ্ছা, তোমার না হয় মাইক খারাপ, বাকিদের তো আছে। মৌসুমি হ্যাঁ আছে তো, হয়েছে শেয়ার।
ইয়েস ম্যাম।
ওকে ওকে। এটা আবার কি হয়ে গেল? এক সেকেন্ড। হ্যাঁ দেখো তো, হয়েছে এবার?
ইয়েস ম্যাম, দেখা যাচ্ছে, স্ক্রিন দেখা যাচ্ছে।
ওকে ওকে ওকে, ঠিক আছে। Okay, so in the last class, we have introduced ion implantation. Now, why did we adopt this additional mechanism for doping the silicon? Diffusion was sufficient, but we came across some major disadvantages in case of diffusion. What are those? Mainly is the lack of flexibility and also accuracy. Then it is a very high temperature process, so for that we had to be restricted in case of choosing the mask. We have to choose the mask material that withstand that high temperature, like 1200 degrees Celsius or something like that, without chemically get deformed. Another one is this diffusion mechanism. It was very prone to contamination. Now, this ion implantation process claims that it has overcome all these three deficiencies that we faced in case of diffusion. And we have seen that basically we can adopt a Gaussian distribution, or N versus X curve takes a Gaussian shape in case of ion implantation. But what was the problem? The problem was, it is fine that the doping profile is taking a Gaussian shape, which is a well-known mathematical distribution, and hence it becomes very easy to model it and hence to predict it or getting the actual profile shape. But side by side, this ion implantation mechanism, it is making silicon amorphous. So, if silicon becomes amorphous during this ion implantation process, then the ions can be implanted within the slab of silicon, but unless and until the silicon regains its crystality or crystal nature, the dopants cannot be electronically active. So, in order to regain this crystallinity, we adopt a separate process, which is ion implantation is followed by that process, which is called rapid thermal processing or rapid thermal annealing. That is, we ramp up the temperature to a very high temperature, very in a very high speed, and then cool it down rapidly. So in that way, what happens? Um, the amorphous silicon, it regains its crystality and incorporating the already implanted ions in the required substitutional sites to make those dopants electronically active, so that it can modulate the conductivity of the electron of the silicon slab. Fine, but the consequence of that is, when we are increasing the temperature, whether we are doing it rapidly or slowly doesn't matter, but we are increasing the temperature. So the low temperature ion implantation is followed by some high temperature anneal process, and during that anneal process, this is actually the anneal process. During this anneal process, the dopants are bound to spread within the silicon further. So some amount of diffusion is taking place during this anneal step. We cannot avoid that. And that is why we had to know about the mechanism of diffusion as well. We cannot discuss diffusion as a whole. So ion implantation must be followed by diffusion during the anneal step in order to get a set of electronically active dopants within it. Now the question comes, if the diffusion is taking place somehow, then obviously the Gaussian profile or the penetration depth that we were talking about must get distorted or must get exceeded. So in that case, what we can do, we can implant the ions up to that position, which is a little bit less than the desired junction depth. So after the diffusion, that is after the spreading of those dopants within the silicon, while the silicon is regaining its single crystal nature, the junction depth cannot be exceeded. So that is one technique that we can do. And since we are doing that anneal step, adopting the rapid thermal processing, the duration at which the silicon remains at high temperature is very, very less. So the diffusion happens, but in a very controlled manner. So it doesn't get very much deviated from the Gaussian profile that it has taken. Now today what we are going to do, we have seen all this in last classes. So today we are going to see a system of ion implantation, or what is called ion implanter. So basically, what is that? Now we know the ion implantation mechanism. That is, high energy dopants or high energy ions are bombarded towards the silicon surface in order to dope the silicon. So first of all, what we need to generate that particular ion. If we want to dope it with arsenic or boron, accordingly we are going to generate that. Then we have to bombard it, those ions, we have to bombard it with high energy to the silicon surface, or alternatively you can say we have to accelerate the ions into a beam at a specified energy. And when it falls, that beam falls on the silicon surface, it scans the wafer under the beam. Suppose we have the silicon wafer like this. This is a silicon wafer, and we have got a mask over here. This is the desired windows where the ions are needed to be implanted. So the profile would look like something like this. So in this case, basically, if we see the top view, then this region has got a finite area like this. So we have to make sure that the ion beam scan each and every portion of this area. So that is what we call as the scanning the wafer under the beam. And then ultimately we have to stop when a set dose is achieved. Now remember one thing, this ion implantation itself, this is the step just before the annealing. This entire mechanism of ion implantation is a low temperature process, but this must be followed by a high temperature anneal step. So ion implantation basically is a two-step process. At first we have to do the simply ion implantation, and then we have to follow it with the anneal step, which is a high temperature process. Now let us see the schematic of this particular ion implanter. Now so far from the mechanism we have learned that what we need to generate the ion, that is an ion source. Okay. Next what we need? Next we need some mechanism that allows the ion beam to strike the wafer with high energy. To strike the wafer with high energy. So basically these two we have to achieve through ion implanter, or from the nutshell of ion implantation we have known this far. So let us first talk about this ion source. How can we generate the ions? So let us look at this diagram. Here it is an ion source. It is basically a chamber inside which the gaseous source of the ions are taken. Not gaseous source of the ion, the gaseous compound containing that dopant, it has been taken. And how can we generate the corresponding ions? We can generate the corresponding ions by ionizing that source gas. As simple as that. We have to ionize it somehow. So how to do that? And when the gas within this chamber getting ionized, we call that the ions, we call that a plasma has been generated. So basically plasma is nothing but when ionized gas, it contains of several types of ions within it. Now why am I saying that several types of ions? Let us take an example of BF3, boron trifluoride. It's in its vapor form is taken within the chamber, and when it is hit by electron, the collision between this ion and collision between these molecules with electrons, it produces several types of ions and fragments of atoms. Like it can produce atomic boron, it can produce B plus, it can produce BF2, it can produce BF2 plus or F plus. So all these are positive ions, and these two are the neutral particles. All are produced during this ionization or ionization of BF3. Similarly, if we go for this arsine or phosphine or diboron, a mixture of ions are going to be formed. Now, in this particular case, for ion source, gaseous source are preferred over any liquid or solid source. The reason is pretty simple, because ultimately we have to ionize the whole thing. So in this case, but we have to keep in mind that in case of arsine or phosphine, while we are dealing with that, those two gases, they're highly poisonous and one of them is explosive. So we have to take a proper measure in order to use them within the gas chamber. So the dilution mechanism that we have talked in the last class, that we dilute it with 99.9% of argon or some other inorganic, and sometimes the dilution can be done with the aid of hydrogen. So a mixture of that gas is placed within the chamber. Now, how the electron which is going to be collided with the gas is produced? Basically, this ion source contains of, suppose this is the schematic of the ion chamber. Within here, there is a cathode, or what we call as the electron emitted filament. So with the proper bias, this is basically a cathode, with the proper bias it emits electrons, and there are anodes at two sides of this chamber, which is maintained at a corresponding negative potential, or negative energy is given over there. So once the electrons are emitted by this filament, these electrons get easily attracted towards this anode due to the opposite potential. Now, during its travel path from this filament to this anode, it collides with the gas. And during this collision, the ionization of the gas will take place, along with the secondary emitted electron, which again take part in the collision and becomes responsible for generating these kinds of ions. Now, in some cases, what we want to increase the number of ions within it. Obviously we want to increase it, and when we are increasing the number of ions within the chamber, it is called that as if we are increasing the ionizing efficiency. Ionizing efficiency. So to increase the ionizing efficiency, we need to increase the number of collisions. And for that purpose, in addition to this arrangement, a magnetic field is applied. Magnetic field that has been applied here in the perpendicular direction, in such a way so that the emitted electrons, they are subjected to a helical like motion, like this. Instead of moving it like this in a zigzag manner through collisions, it does suffer, one single electron, it does suffer collision, but its overall motion becomes helical, so making its duration in this gas region more compared to that without the aid of magnetic field. So in that case, what happens, since its duration within the gas becomes high, the number of collision becomes automatically high. So in this way, this is a means to increase the ionizing efficiency, and more ion are generated. So in this way, the ion source, it generates the corresponding ions. Now the question comes, I'm taking this particular example of BF3. You can see that here three types of ions are already formed. If we consider singly charged ion, there is a possibility that it can also create B++ or doubly charged ion, or BF2++, like that. There is a possibility. But if we see the ratio in terms of the number of ion production, then we can see that the ratio of B plus is to B plus plus is approximately 10 is to 1. So the probability of generating this B plus plus ion is very, very less compared to that of the B plus ion. So we always talk about this B plus ion. Now here a question comes in our mind, that since all are positive ions and not fluorine plus, but since these are the positive ions and it has got boron within it, so whether we are going to accelerate the mixture of this ion and send it to strike the wafer, or we need to select just one ion and create the corresponding ion beam and make that ion beam to strike to this wafer. But before doing that, all we have to do, we have to first extract the created ions. from this chamber or from this ion source. First we have to extract it. So for the extraction purpose, there is another set of electrodes which is shown like this. It is given a particular potential. It is maintained at a particular potential. Since it is a positive ions we are extracting, it is set at a negative potential. So it attracts, and here at this point there is an orifice. Now the shape of the orifice might be circular, and in some cases it might be rectangular depending on the system. So from here, due to this potential or this energy that is given to this extraction electrodes, the ions are attracted and they are emitted from this orifice. So it is creating an ion beam. Now the question comes whether we are going to allow this ion beam to strike the wafer or not. The answer is no. We want one particular ion to strike the wafer. The question is why. You see, here the mass of these ions comes into play. The B plus ion obviously is much more lighter compared to that of BF2 plus ion. So even if we apply the same energy and try to accelerate it and then send it towards this wafer surface, BF2 plus ion, due to its heavier property, it will penetrate less amount within the silicon semiconductor, and B plus ion that will penetrate more distance within the silicon. So in that case, with same amount of accelerating energy, the penetration depth for two ions will be different. So from ion to ion, it differs. And in that case, it becomes very difficult to control the entire profile or to maintain a single junction depth, because we cannot accelerate different ions by different energy. If we try to do that, then again we have to go for the mechanism that basically separates those ions from each other. So the separation is necessary. So for that, this kind of arrangement, which is called mass analyzer or mass separator, that has been used. So let us see what exactly this mass analyzer or mass separators does. Let us focus on this particular diagram. Here, a magnetic field is applied in perpendicular to the direction of the screen. So this is the direction of the incident ion beam, and this is the magnetic field which is perpendicular to the screen. So under the effect of this magnetic field, the ions are obviously going to be deflected in this direction. Which direction? That makes a 90-degree angle with both the magnetic field and the direction of the incoming ion. Simple. So, and the force that is experienced by each ion is given by simply Q into V cross B, where B is the magnetic field strength and V is the velocity of the incoming ion. Now, this must be balanced by the centrifugal force that is experienced by each ion. And what is the expression for centrifugal force? It is mv squared by r. Now, what is this r? This r is the radius of the trajectory. You see, the radius of this trajectory. And you can see that this r varies for different masses. Now let us consider this equation as 1, and there is another equation which basically deals with the kinetic energy of the incoming ion. Here this is the external potential. If V is the external potential or the potential that is given to this extraction electrode, suppose it is V external, and here I can write it like this, then we can say that this half mv square is equal to QV external, or simply QV. So this equation I am giving as number 2. Now from 2 we can directly get this expression for the velocity. What is velocity? It is nothing but square root of 2QV external divided by m, where m is the mass of each ion and this V external is the potential that is given to this extraction electrons. Now if we combine this 1 and 2 in this manner, suppose from 1 we can write R or something like, let us say this R. R is equal to mv square by qvb. Now why vb? Because v cross b is vb sine theta, and what is the angle between these two? The angle between these two is 90 degrees, so sine 91, so that becomes simply qvb. Or this 2 will get cancelled, r becomes mv by q. Now if we replace this expression for v from here, then we can write it like this: m by qb root over 2q v external divided by m. Okay, so ultimately we are getting the expression for r, that is this trajectory, the radius of this trajectory path is something like this. So you can see that directly this R is directly proportional to M, that is mass of the ion. More is the mass, more will be the value of R. So, and less is the mass, less will be the value of R. So, if we look at this trajectory now, we can see that this heavier ion, it has got larger value of R, but the lighter ion, it has got the smaller value of R. So in this way, depending on the mass as well as the charge state, that is whether it is singly charged or doubly charged, so depends on this ratio m by q, this factor R is going to be determined. Exactly, that is what is happening here. So due to this mechanism, or this mechanism is responsible for separating the beams of ions, and each beam consists of each type of ion. Like BF3 would be the heavier ion here, so this blue line that might correspond to BF3 plus, and this middle line that might correspond to B plus, and this one, this might correspond to more lighter ion, maybe F plus. Now, if we manage to place an orifice like this in that position, so that only the ion beam corresponding to this B plus passes through and the rest of the ion beams are getting blocked, then we are end up with an ion beam consists of a single type of ion, or consists of our desired type of ion. In present case, that is the ion we have chosen is B plus ion. So we have managed to create a single ion beam consists of a single type of ion. Now let us go back to this diagram again. So from here we have managed to a single beam of ion. After that, we are subjecting these ion beams through an accelerator. It is an electrical arrangement that basically accelerates the ion with high energy. Now after that, when it is emerging from this accelerator, a focus is placed. Now what is the purpose of placing this focusing arrangement? Because you see here the ion beam, it consists of all similar type of ions, or all like charges, that is positive charges. So these positive charges, they tend to repel each other, right? So if they are tending to repel each other, then obviously there is a tendency for the ion beam to get diverged in both direction, to spread in both direction. So in this case, we need to focus this diverging nature to produce a very pointed beam, as is shown over here through this focusing arrangement. Now question is, what is wrong if we allow the beam to get diverged? First problem that might come, that these diverge beams, so some of the ions, it might collide with the wall of the container through which it is passing, and when it collides with the wall of the container, some little amount of sputtering may happen. It might sputter some chunks or some impurities from the container, and that might get mixed up within this ion beam. That is one problem, and it becomes some impure ion beam instead of a very pure ion beam. So the impurity might comes into this ion beam. Next is, when it is getting diverse, it is very difficult to cover or to restrict only within this window. If it is getting diverged, it might happen that when it reaches the wafer, the divergence is something like this. So it spreads in here and in this direction also. Although we are using the mask, but still there is a possibility that it might penetrate the mask and enter the silicon. So we don't want to take that risk, and we want to concentrate the beam, or we want to restrict the beam within this area, within this windows area. We cannot allow the beam to fall or to exceed the region boundary of this particular area. So that is why this focusing arrangement is needed. After that, there is something which is called a neutral beam gate, followed by a neutral trap. What is this? Sometimes some neutral particle might appear within this beam. It might happen that some of the positive ions within that ion beams gets neutralized somehow by some error, and we do not want that neutral atom, or maybe some neutral atom comes from the container, or comes from the, not container, from the chamber through which it is progressing. It might come in form of some impurities. So, or maybe it might happen that maybe some other neutral particle might come up here. So we need to strain the ion beams from those impurities or from those neutral particles, and that can only be done if we try to deflect the ion beam a bit. Now, deflection by means of applying an electric field across it can only take place in case of a charged particle. The neutral particles cannot be get deflected under an electric field. So in that way, only the positive ions will get deflected, and that is why it is called a neutral bend also. This particular thing is also called neutral bend. And the neutral particles, they won't be able to get deflected, and those neutral particles ultimately will be collected by a mechanism which is called simply neutral trap. So now the ion beam consists of solely B plus ion. Now this B plus ion, there are some sets of plates like X and Y scan plates, we call them. These are basically called the beam sweeper. Beam sweeper. Now, what do we mean by this beam sweeper? From the name itself, we can tell that it has got something to do with sweeping the beam in every direction. So basically, we need to move this beam in horizontal direction as well as in vertical direction in order to cover this entire region. So from here to here, it will scan from here to here, then move here, then it will again scan from here to here. So in this way, this entire area, this entire window, that must be exposed to the incoming ion beam, and that can only be done by sweeping the ion beam across this whole area. So in this way, we have managed to sweep it. You see, there are basically two sets of parallel plates. One is here, where the plates are horizontal plates, but the electric field across it, it is basically responsible for moving the beam vertically. So that is why it is called VV, the corresponding potential. And here, this is the position of the pair of plates, and here across this, the potential has been applied, and it is responsible for moving the beam in horizontal direction. So with the aid of these two sets of plates, we are able to scan the entire area of the wafer. And if we go with this kind of arrangement, the scanning speed is extremely high in this case. Now, there is a problem with this system alone. When the problem arises, when the current or the beam current is greater than 1 milliampere and beam energy is less than 50 kilo electron volt. So, if this condition arises, then beam tends to expand after emerging from this neutral band. So here the distance increases if we use these two sets of plates, two pair of plates. The total distance increases, but so there is a probability to expand the beam more in this case. But if we omit one set of plane and place the neutral band just over here, then the total distance becomes very less. So we are using, or we are sacrificing one pair of plates in order to maintain the focus of the beam. So here, as we are seeing, only horizontal beam movement is possible through these plates. But we need to scan the wafers vertically as well, otherwise the whole area won't be covered. So in that case, what happens, the wafers, a group of wafers, they are mounted on a rotating carousel. And this is rotating with this speed, and they are taking care of the movement of the wafers in vertical direction. So this, by sweeping, here the beam is swept only in the horizontal direction, and this rotating carousel, they are responsible for the vertical movement of the wafers in order to cover the entire area to be scanned properly. So in this way, it strikes the wafer. Now the question comes that when are we going to stop this entire process, or what we call as the dose control mechanism. So we know in case of ion implantation, two are very important parameters. One is obviously the penetration depth or junction depth, and second is the dose, that is phi. So after a certain dose or after a desired dose has been achieved, we have to stop this mechanism. So how can we know about this, whether the dose has been reached or not? So let us first see that what parameters we have got in our hand of the system operator. Basically, beam current or I is the parameter the system operators can have their hand. You can see during this extraction of ion, this potential can be fixed or can be decided by the operator, and basically this potential is responsible for the kinetic energy or for the velocity. So because it is kinetic energy is equal to Q into V external. So this is responsible for determining the velocity. Now what is current? Basically the rate of flow of charge. So by controlling the velocity with by means of this V external, we can basically decide the value of, or we can basically tune the value of the current that is coming out from this chamber. And after that, we are accelerating it with a specified energy. So that is something that the system operator has in their hand. Now let us consider that the charged state of ion. charge state of ion that is given by N. What do we mean by charge state of ion? That means whether it is singly charged or doubly charged or quadruply charged or triply charged, something like that. So here in this particular case, this N is equal to 1 because we have chosen this B plus ion, and this plus means it is singly positively charged. So that is the charge state of ion that is given by N. So now number of ions hitting the silicon surface per unit time, that can be given simply by I divided by NQ, where AQ is the electronic charge, I is the total current, and N is the charge state. If it is 1, then it simply becomes I by Q. So that is the total number of ions hitting the silicon surface per unit time. Rate of flow of charge is current, so that is divided by the charge of a single ion. That actually gives you the number of ions that is hitting the surface per unit time. Fine. Now if the total duration of the process, is T, then the number of ions hitting the silicon surface in the time T is given by IT into NQ. Okay, this is the total number of ions hitting the entire exposed area. And if this entire exposed area is A, the number of ions per unit area is given by IT by NQ divided by A. So what is this? This is number of ions per unit area, which is simply the dose or phi. So here you notice one thing, we can basically control this dose by controlling either beam current or the duration of the entire process, or by both. So obviously we want to increase the throughput. So in that case, what we can do, we want to decrease this time duration. So in that case, we have to increase this beam current, that is the potential of extraction. So in that way, if we can manage to do that, then we can achieve the desired dose in a very short amount of time. And if we cannot increase the beam current to a very high value, then we have to increase the amount of time of the entire process. So by tuning these two parameters, that is the beam current I and the time duration, basically we can tune or we can control the dose. Now the thing comes that when we are going to stop performing this mechanism, or when we are going to stop this ion implantation process, once the dose has been reached, so we must have a mechanism that measures this beam current at each state for each time duration. So that arrangement is what is called as the Faraday's cup. So here this wafer is placed inside an arrangement which is called Faraday's cup, which measures the beam current. This measures the beam current over a certain amount of time. So basically, see, it is followed by an integrator circuit. So basically what it does, it calculates dose at each stage by simply integrating the entire current. So the phi, it was IT divided by A into NQ. A is constant, it is taken out of the integral, and over the time it has been integrated, and at each stage we check the corresponding value of dose. And once the desired dose is achieved, the mechanism is stopped. The process is stopped. So in that way, we can get a proper ion implantation mechanism. Now in case of here, as you can see, this rotating carousel, that is also responsible for making this entire ion implantation process very efficient in the terms of throughput, because you can see, depending on this casserole size, the number of wafers that are mounted on it can be increased. It is not a single wafer process, unlike the case in rapid thermal annealing. It is a multiple wafer. We can implant to multiple wafers at a single stage or at a single go. So that has got high input. Now, so in this way, we can basically control the dose of the ion implantation, and as well as we know when to stop this entire mechanism. So through this, now as we look back to the schematic of this ion implanter, what we have basically, we have got an ion source. It is immediately followed by a means to extract the ion source, to extract those ions from this chamber. Then obviously the beam has to be diverged a bit, but here the focusing arrangement is not placed, because here at first we need to separate these ions based on their mass. Why? Because this is basically a soup of different kinds of ions. Might be a mixture of B plus, BF2 plus, F plus, sometimes B plus plus, F plus plus, and all that. So this extraction mechanisms is immediately followed by the mass analyzer, or sometimes it is called a mass spectroscopy arrangement. And here a single ion beam has been created, which consists only of the desired ion. This is followed by the accelerator mechanism that accelerates the ion beam with desired energy, and it sends it towards the silicon wafer. This is followed by a focusing arrangement which focuses the electron, the diverging electron beam. Then it is followed by a neutral bend to separate the neutral particle if it appears within these ion beams, and it suffers a minor deflection. And these are the neutral trap that collects the neutral particles. After this, there is a beam sweeping arrangement that can either consist of two pair of plates that is responsible for moving the beam in horizontal as well as in vertical direction, and in some cases we might use one set of plate and followed by a rotating carousel. And that rotating carousel or wafer mounter that is placed within a Faraday's cup. What is the purpose of that Faraday's cup? That basically measures the beam current. And why do we need to monitor the beam current at each stage? Because that beam current, by monitoring it, we can calculate the dose, and at each stage to monitor the dose, we can know when to stop the ion implanting process, or when we have achieved the desired dose or desired doping concentration. So this is the ion implanter, the mechanism of ion implanter, and the system which is responsible for ion implantation. So this basically ends our discussion today. If you have got any question regarding anything, you may ask. কারোর কোনো জিজ্ঞাসা আছে, কোনো কনফিউশন আছে এখানে? ধরে নিচ্ছি নেই, তাহলে আমি স্টপ প্রেজেন্টিং করছি, আর একটু ওয়েট করো। কিছু বলছো?
Yes ma'am, yes ma'am. ওই লাস্টে যে ফ্যারাডে ক্যাপ ছিল ওই পোরশনটা আরেকবার বলবেন?
ওকে। স্ক্রিনটা কি শেয়ার হয়েছে?
ইয়েস ম্যাম।
ওকে ওকে, আচ্ছা মিউট করো হ্যাঁ। আচ্ছা, ফ্যারাডে কাপটা বেসিক্যালি কি করছে, আর এটা কিন্তু ফ্যারাডে ক্যাপ নয়, ফ্যারাডে কাপ, হ্যাঁ, CUP, ফ্যারাডে কাপ। ফ্যারাডে কাপটা বেসিক্যালি কি করছে, এখানে যে বিমটা ইনসিডেন্ট করছে সেই বিমটা ও কারেন্টটা, সেই বিম কারেন্টটাও মেজার করছে। এবারে মেজার করে ও সেটাকে ওভার দ্য টাইম ইন্টিগ্রেট করছে। মানে বেসিক্যালি আমি কি করতে চাই, যে মানে প্রত্যেকটা স্টেজে আমরা কারেন্টের ভ্যালুটা সাম ইন্টারভ্যাল অফ টাইম আমরা ওটা চেক করতে থাকি। কেন চেক করতে থাকি? বিকজ এই ডোজের এক্সপ্রেশন আমরা কি বার করলাম, এই ডোজের এক্সপ্রেশন হচ্ছে সিম্পলি বিম কারেন্ট ইনটু টাইম ডিউরেশন ডিভাইডেড বাই NQA। এবারে A কনস্ট্যান্ট, N ও আমরা জানি, Q ও আমরা জানি। সো এখানে বেসিক্যালি ভ্যারিয়েবল হচ্ছে দুটো প্যারামিটার, একটা দিস বিম কারেন্ট, একটা হচ্ছে এই টাইম। এবারে টাইম, ওভার টাইম বেসিক্যালি উই আর ইন্টিগ্রেটিং ইট। তার মানেটা হচ্ছে যে আমরা এখানে বিম কারেন্ট এট ইকুয়াল অ্যামাউন্ট অফ টাইম, সাপোজ T1 টাইমে বিম কারেন্ট হলো I1, দেন T2 তে I2, দেন T3 তে I3. So basically what we are doing, we are measuring this current over this whole interval of time. So basically আমরা এটাকে IDT করছি, ইন্টিগ্রেশন করছি। সো এই ফ্যারাডেস কাপ কি করছে, ও অ্যালোন এই বিম কারেন্টটাকে মেজার করছে। এই বিম কারেন্টটা এবার একটা ইন্টিগ্রেটর সার্কিটের ইনপুটে দেওয়া হয়েছে, আউটপুটেও সিম্পলি ওই ইন্টিগ্রেটরের যে করেসপন্ডিং ভ্যালুটা সেইটা ওখানে দিচ্ছে। এবারে এইটা আমরা যখন করেসপন্ডিংলি এইটা আমরা পরপর যখন চেক করতে থাকছি যে কত ডিউরেশনের পরে এই ভ্যালুটা, এই ফাই এর ভ্যালুটা অ্যাটেন্ড করছে, ডিজায়ার্ড ফাই ভ্যালু। সাপোজ আমি এখানে চাইছি যে x পার সেন্টিমিটার স্কোয়ার, এইটা আমার ডোপিং ডোজ হবে। তো যতক্ষণ না এই x পার সেন্টিমিটার স্কোয়ার ডোপিং ডোজটা অ্যাচিভ করে যাচ্ছে ততক্ষণ আমি প্রসেসটাকে কন্টিনিউ করবো। যেই আমি দেখলাম এখানের ভ্যালুটা আমার x টাকে অ্যাচিভ করে গেল, অমনি আমি এটাকে অফ করে দিলাম, এই মেকানিজমটাকে স্টপ করে দিলাম। সো বেসিক্যালি ফ্যারাডে কাপ কিছুই না, জাস্ট এই বিম কারেন্টটাকে মেজার করে তাকে টাইমের ওপর ইন্টিগ্রেশন করে দিচ্ছে, মানে যাতে করে আমরা এইটার মেজারমেন্ট বা এইটার এই ডোজ ক্যালকুলেশনটা অ্যাকর্ডিংলি করতে পারি, বা ডোজটা মনিটর করতে পারি ফ্রম টাইম টু টাইম। ওকে, আর যদি আমরা ডোজ মনিটর না করি তাহলে আমরা বুঝতে পারবো না when to stop that mechanism or when to stop that ion implantation. বুঝা গেছে?
ইয়েস ম্যাম।
ওকে, ঠিক আছে, তাহলে আমি অফ করছি, তোমরা একটু দাঁড়াও, অ্যাটেন্ডেন্স নিয়ে। ঠিক আছে, তোমাদের থ্যাংক ইউ আসার জন্য।
থ্যাংক ইউ ম্যাম।
ওকে
ম্যাম।
থ্যাংক ইউ। লিভ করে যেতে পারো।